How do we graph and use the natural base functions? Well, it'd help if we knew what a natural base was, right? What the natural base is, rather. Well, to figure out where it comes from, we're going to fill out this table. Okay, so we have some x values and just like x and y. So this is the function that we're going to plug x into. 1 plus 1 over x raised to the x. So in this first thing, it would be 1 plus 1 over 10, all raised to the 10th power. Okay, and that comes out to 2.594. Now 10 squared is 100, so we would do 1 plus 1 over 100 raised to the 100th power. Now it comes out to 2.705. And so on until we filled out the entire table. So as we fill out this table, we get 2.717, 2.718, 2.718. So, well, we get the same thing twice whenever we round a little bit. Like the fourth decimal was a little bit different. But, so, do the values appear to be approaching a number? Well, what does that mean to approach a number? So, let's think about this. What are the x's doing? The x's are getting bigger and bigger and bigger, right? By a lot each time, by a power of 10. So, eventually those x's, they're just going to infinity, right? So we say as x goes to infinity, the function 1 plus 1 over x raised to the x is approaching some number. And that number is 2.71828. And then this decimal goes on and on. What's special about this number right here? Is E. E is the natural base. Okay, it's the base of a natural log, which we haven't talked about yet. But this E is a super important number that occurs over and over in nature. And it all comes from this function right here. 1 plus 1 over x raised to the x as x goes towards infinity.
It's going to be the 2.71 in the 9.
Whenever we're graphing natural base functions, all of the same rules apply, okay, as all of the other exponential functions that we've been doing. So this a, what is a going to do?
Makes it stretch.
That's my stretch, compress, or if it's negative, it reflects. What does the h do? Left and right or up? Left and right, yeah. K is up or down. Okay, so the only thing that looks a little bit different is the E. And notice that it's e to the r. So e to the r, all of that acts as my new base. Okay, that's going to be my B. It's my B. All right. Now, let's look at this example. Y equals 2e to the 0.5x. Oh, sorry. Before we get into that, I want to talk about r a little bit more. So, we saw that growth is whenever the base is greater than 1, right? Well, anytime you raise e to a positive number, you'll get a number greater than 1. Okay? So in order for all of this to be greater than 1, r just needs to be positive. So if r is positive, so if r is greater than 0, you get growth. And e to any negative number will give you a number between 0 and 1. So if r is less than 0, it's decay. So looking at this example, 2e to the 0.5x, will that be growth or decay? What's r in this case? R is 0.5. Is 0.5 greater than 0 or less than 0? It's greater, so this is going to be a growth. Okay? So, we always start with 0, 1, 1b. Okay? Now, today, that b, 0, 1, 1, the b is e raised to that power. So e to the 0.5. And we use our calculator to figure out what e to the 0.5 is. So we have the points 0, 1, 1, 1.65 after some rounding. Okay, now, the only transformation to this function was this 2. What does that 2 do? It's a stretch by 2. How do you stretch by 2? Well, you multiply the y values, right? So these y values get multiplied by 2. So you should still have that number in your calculator. Just hit times 2. All right, and now we have new points, 0, 2,
3.3.
1, 3.3.
Yes.
Okay. Did the asymptote get shifted? No, because there's no k, right? Like there's plus 0, so it didn't shift up or down. So I have this horizontal asymptote at y equals 0. I can plot my points 0, 2, 1, 3.3. So I knew it was growth, and look, this has to be growth. The only way to go through these 2 points is to rise through them towards the right. So get real close to the asymptote, rise through the points.
Couldn't you come down?
And what's the domain of this function? All real numbers. Now the range comes from the asymptote. The asymptote is 0. The function sitting on top of it, so all the y's are greater than 0. So y equals e to the negative x plus 1. What's the only transformation here? It moves up 1. Okay, so I need to start by figuring out 0, 1, 1b. So I have 0, 1. And now here's the biggest mistake people make. They write 1 e to the negative x. But you can't have the x like as a number. This is my r, that just little negative thing. So this is e to the negative 1. Okay? E to the negative 1 is 0.368. So I have 0, 1, 1.368. And then the only thing that I have to do to these y values is add 1 because we moved up 1. So I'm going to add 1 to these y's. So my final points that I'm going to graph are 0, 2, 1, 1.368.
Wait, so like...
Since we shifted up 1, what else got moved up 1? The horizontal asymptote. So now this is at 1. So I've got a horizontal asymptote at y equals 1. Was this going to be growth or decay? Decay, because r is negative, right? This r is negative 1. Well, let's see if that looks right. 0, 2, 1, 1.368. So this second point's lower, so it'll fall.
So if the second point's lower, it falls, and if the first is
Okay, so that looks right. What's the domain of this function? All real numbers. What's the range? Y is greater than 1 because it shifted up 1. So whenever we simplify natural base functions, it's just like simplifying anything with exponents, okay? We're just going to use our basic exponent properties. So let's look at A. We have 4e cubed times 2e to the 5th. Well, the numbers just multiply. 4 times 2 is 8.
Yeah.
And then if these things have the same base of e, what do you do with their exponents, 3 and 5? You add them. So that's e to the 8th power.
So it's 8. Okay, so you multiply the...
Okay, so whenever you're multiplying, you add the exponents. So whenever you're dividing, what should you do to the exponents? Subtract. So 10 divided by 5 is
2.
2. And now if you subtract those exponents, you get e to the
Negative first.
negative 1. Now, it's not completely simplified if you have a negative exponent, right? A negative exponent needs to move. So this is 2 over e to the first power, so just 2 over e.
That's the answer.
Now, one common mistake people make with this is that they write 1 over 2e. But notice that the 2 wasn't being raised to a negative, right? This 2 silently has like a 2 to the first power. Another way to look at this is, what's 10 divided by 5?
2.
Okay, so the 10 and 5 cancel and you have 2. And then if you take e squared out of e cubed, you're left with just an e. So 2 over e. But I want to show you that subtraction method because that's how we're going to look at d in a second. If you have 3e to the negative 4x and all of this is being squared, well then everything inside gets squared. So you have 3 squared times e to the negative 4x squared. 3 squared is just 9. Now, if you have an exponent raised to an exponent, the exponent properties tell us that we multiply those. So that's e to the negative 8x. I'm running into the same problem here. I've got a negative exponent.
So you put 9 over.
So the 9 stays in the numerator, and this e to the 8x moves to the denominator. Alright, this last example is a little bit more complicated because the exponents are variables. Okay, so instead of just canceling, we're going to have to use the subtraction method. Okay, here we have e to the x, and if I'm subtracting their exponents, that'd be minus all of 2 plus x. I put this in parentheses because I have to subtract the entire exponent. That's e to the x minus 2 minus x. And see, this is important because now the x's cancel each other. X minus x is 0. So I have e to the negative 2. So simplify e to the negative 2. 1 over e squared.
Tell me.
Okay, now as an application of e, the most common application is continuously compounded interest. Okay? If you're ever looking at a problem and it says continuously, this is the key word to look out for. That lets you know that this is the formula that you need to use. A equals P times e to the RT. The PERT formula. Okay?
Hurt?
Continuously, unlike compound interest that's only done like either quarterly or monthly or whatever, continuously means that you're constantly gaining interest on the interest that you've already earned. Okay? Like instantaneously. So, the P is still the principal. E is not a variable. E is a number, right? R is still the rate, and T is a time. The rate you have to express as a decimal. So let's try to do this. You deposit $4,800 into an account that pays 6.5% annual interest, compounded continuously. So that lets me know to use that formula. What is the balance after 3 years?
A equals 4,800.
So A equals 4,800 times e to the rate. What's the rate as a decimal? 0.065 times 3 years. So after 3 years, we have in our account $5,833 and how many cents? 49 cents. So,
They went around with them.
hey, how much interest did we earn?
A lot.
13.
$1,033. So you got to also be careful of what the question's asking. If it asks you how much interest did you earn, then you would have to subtract from your original.
It's the same number.
Okay? But that's how you use continuous compound interest. And that's going to be all for today.